Okay, today is July 18th, 2019. This is the normally scheduled meeting of ITSE 2309. Tonight we are in Module 10, which are data types, and we are continuing with where we left off last night. And where we left off last night, I had just discussed the data type integer. Now, let me review a little bit about integers. Integers are nice. We like integers because integers are absolutely accurate. 3 is 3. There's no decimal, there is nothing, there's no repeating decimal part of it. It's just 3 or 5 or a million, whatever. It is what it is, and that's it. Okay, it's when you get that decimal point that life becomes a little tricky. Now, if an integer happens to have a decimal point, it's fine. We can live with that. We can deal with that fairly easily, so long as it is a fixed decimal point. If it is a fixed decimal point, like, for example, dollars and pennies, I pointed out that actually money is 4 decimal places fixed, but let's say it's 2. It's pretty easy. All I do is multiply it by 100, store it as an integer, and then when I show it to you, I divide it by 100. So I shift the decimal point in, shift the decimal point out, or out and in, I guess, depends. So I would never store $17.32, 17.32. I would store it as 1,732 cents. That's pretty typical the way it's done. Anytime we fix a decimal, it becomes an integer. So anytime it's fixed, it turns into an integer. Let's see. All integers suffer from a vulnerability that is known as overflow. If you get big enough, you run out of room in that integer, and what happens is that it does the old 1968 Volkswagen odometer thing, where it rolls over, as we say, to 0. Okay, what happens is it carries out of range. And where did that problem manifest itself in our 1968 Volkswagen bus? It was at the 100,000 miles, so it was at a power of 10. In a computer, that problem will manifest itself at a power of 2, probably at a power of 2 that is also a multiple of 8. So it would probably be at like the 32 bits. So 2 to the 32nd power is where you will typically get this overflow. And that's a real common place to get it. Let's see, I pointed out that my trick question about what state is farthest east, and ha 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 is a joke, it's Alaska, actually, because Alaska extends into the eastern hemisphere. So since we have east and west, and I liken that to having a positive numbers and negative numbers. So if I say going west is positive numbers, going east is negative numbers, then if you go far enough west, you end up east, and that's the way it works with integers also. If you go far enough, you get bigger and bigger and bigger and bigger, and then all of a sudden you have the overflow where it would have shifted back to 0, but since it has a sign on it, it doesn't shift back to 0. It shifts back to the greatest negative number. And that's real common. Overflow is just a problem we have. The only way to fix that is to get a bigger, more memory, throw at it. The good thing about overflow is that when it does happen, it's fairly easy to detect. It's a big error. Okay, so overflow, what is it? It is a carry out of range. And we can't represent that number because we don't have enough bits. So what happens is it carries out of our range, and we see the result as 0. Just as in your 1968 Volkswagen bus, when you hit 99,999 miles, it flips over, it adds 1, but that 1 cannot be represented. It goes out of the range. And so what we see is 0, but it's really 100,000 miles. Yeah, you don't get a new warranty or anything like that. So that's the deal with overflow. With integers, we have several options that we can use. The most common one is int, and int gives us 4 bytes before we overflow. And so that means that I have 2 to the 31st power, but remember 4 bytes is 32 bits. Because I have positive and negative, I have to represent positive and, negative numbers. So I can only go up to 2 to the 31st power. And 2 to the 31st power. So in other words, I have half the range. And that's something like 2 billion. If you think of it as 2 billion, there's the number, the actual number, about 2 billion. If I'm overflowing that 2 billion, actually 147 million more, which is quite a bit of money if it had money. If I'm overflowing that, I have to go up to a big int. And in other languages, C and Java, for example, we call this a long integer, long int. And that typically takes us up to 8 bytes, very common. Not only did it just double the size, but it doubled it 8 times. No, excuse me, it doubled it 32 times. So now we have just a huge number. I don't even know the name of this number. Let's see, there's thousands and millions and billions and trillions and quadrillions and quintillions. So that's 9 quintillion. Pretty big number. On the other hand, if we just have a little bitty thing that we need to show, if we're okay, if we're within, this one will go up to 32,000. So this one is 2 bytes. A small int is 2 bytes. And that gets me up to 32,000, or 2 to the 15th power, because a byte is 8. So I have 16 bits total. And I have 15 on the positive side, 15 on the negative side. And that's about 32,767 or so. And finally, I have a tiny int, which is 1 byte, one silly little byte, and that will get me from 0 to 255. There is no sign associated with tiny int. Tiny int, you just have to know whether you're talking about positive numbers or negative numbers. With tiny int, if you need to do something that is like true or false, you would use a tiny int, and 0 would be false, and anything that wasn't 0 would be true. Is probably how you deal with it, because basically 1 byte is about all is the smallest that you can allocate. All numbers overflow. Any electromechanical device, pencil and paper, you have a finite amount of paper. Anytime you're representing an integer, you have a finite space in which to implement it. Overflow at 99. So I'm talking about this one years ago. Now they're digital devices, and this just is cheaper to add bits, but sooner or later we're going to run out of bits. All integers will overflow, even the newer ones that they claim won't. They have so many bits in them that it's just going to be a lot more miles than your car has. Anything with a fixed decimal is an integer. And then I show how to demonstrate a number with a fixed decimal. So here's an example. I could have used numeric here instead of decimal. I could have written the word numeric. It would have been the same thing. I think decimal is preferred, and I believe that numeric is being phased out. So if you say it is a decimal 8.3, that means that I have at least enough room for 8 base 10 digits. And 3 of these digits are to the right of the decimal place. So it may contain 8 digits, it doesn't have to, 3 of which will always be to the right of a decimal. We have a fixed decimal point, therefore it's an integer. And then I talk about how big it is. and so on. And overflow. When you overflow, you carry to the left out of range. Everything will overflow. If you get over 8 digits, very far over 8 digits, I don't know, it probably won't happen right immediately. You might be able to go a little bit higher just because of the base 2, base 10. I have a feeling that this one is going to allocate 4 bytes. So I can probably go up to quite a bit larger than that, but somewhere up there I'm going to overflow. Okay, floating point. Floating point is a little more problematic. Floating point, consider some fractions. Do they terminate or do they repeat? So 1/2, by the way, the dash t means it terminates. 1/2, that terminates, that's 0.5. 1/3 repeats, that's 0.33333. 1/4 terminates, 0.25. 1/5 terminates, that's 0.2. 1/6 repeats. 1/7 repeats. 1/8 terminates, that's 0.125. 1/9 repeats. 1/10 terminates, 0.1. What's the rule? Well, we're in base 10. Base 10 has 2 factors, 2 and 5. If the denominator contains any fraction, any factors other than 2 or 5, it will repeat. For example, 3 is not a factor of 10, therefore it will repeat. 4 as a factor of 2, 5 a factor of 5. 6, 2 times 3, it will repeat. 7 is prime, it will repeat. 8 is 2 times 2 times 2, it will terminate. 9, 3 times 3, it will repeat, and so on. So if I want to know if it will repeat. A computer represents numbers in base 2. A floating point decimal that has anything except factors of 2 in the denominator will not terminate. So 1/4 will terminate, 1/8 will terminate, 1/16 will terminate, but 1/10 will not terminate. So something like 0.2, 20 cents, will not terminate because that is 2/10, and 10 has a factor of 5, and 5 is not a factor of the base. So that will not terminate. Well, if it doesn't terminate, if I'm working with it, I have to terminate it. Someplace out there, I'm just going to have to chop that thing off. So if I try to represent 20 cents as a binary number, as a binary floating point number, I'm going to have to chop it off. As soon as I chop it off, I'm going to introduce an error. It's kind of like 1/3. If I deal with 1/3 as a decimal, I'm going to get 0.333333333 forever. Sooner or later, I've got to chop it. When I chop it, I introduce an error. This is called underflow. Underflow is far worse than overflow. Overflow is a drastic error. You know, I was trying to pick up something on Monday night, and it was just a little bit too heavy for me to pick up, and I wrenched my back. Had that been something like a car, and I was trying to pick up a car, I would have known. I would have said, there's no way I can pick it up. But it's those little things that get you. And something that's really way outside of my ability to pick it up, I'm not going to try. Overflow, when you get overflow, it's obvious. You add 2 numbers and boom, you got 0. Underflow is an error that's so tiny that it's difficult to see. It's difficult to detect. Overflow I can detect. I add 2 positive numbers, I get a negative number, duh, I've got overflow. Underflow is such a tiny little error, it's hard to spot. Overflow doesn't happen very often. When it does, gee, it's in your face. Underflow happens on almost every floating point calculation and adds up. Okay? Don't use float. So floating point, this would be like, let me see. Don't use real, it is depreciated. Let me see if I say this. Did I show this somewhere in here? I guess I should have given you a demonstration of float. Let me do that now. New query, create table. Create table X, give it a name. Here is the, and float F. There's a floating point number. There is an integer. Its name is I. I suppose I should give it something to use. That should keep it happy. Oh, wait a minute, I'm backwards here. Sorry. You know, when I do that, somebody needs to tell me, Dr. Smith, you're writing in C code again. In C, the type comes first and the variable comes second. Variable type comes next. So F is a float and I is an integer. So this is what we're talking about here. Don't use real here. And let me see. D is a decimal. How many digits do I want to give it? Let's give it 7 base 10 digits. So it will be at least big enough to contain 7, or we'll give it 4. 4 base 10 digits. 4, that means it's got to be a maximum of 9,999. So that's the biggest number that I have to be allowed to put in there, or that many different numbers. Of these, how many are to the left, excuse me, to the right of the decimal place? Now, I can say more than 4 if I want to, and in that case, it would just be, if I said, you know, 7 places to the right of the decimal, then it would be 0.000 and 4 digits. So typically you don't. I could say that, but this one has 2 to the right of the decimal. So what would be valid values that I could put in there? So I could say that D is, what about this? Could I say it was 1,000? Yeah, that'd be okay. Could I say that it was 9,000? No, it would not be okay. Could I say it was 10? Yeah, I could say it was 10. How about 99? So I could say that D is 99. Yes, because there's four digits, and of these, 2 of them are to the right. So what if I said 99.99? That would be okay too. But if I added another digit to that, it wouldn't be okay. Questions? What if I said D gets 999? That would not be correct, because I'm saying that I have 4 total and 2 are to the right of the decimal. Since there is no decimal, it is assumed that it's 0.00, and that is a 5-digit number. And so that risks overflowing the memory I have allocated. So if I want to store this value, I've got to push this up to a 5. 1, 2, 3, 4, 5. A little bit of floating point. Floating point is stored in scientific notation. And that means that I store it with a base and an exponent. And what happens is if I talk about a number that is really, really big, I'm talking about 2 times 2 times 10, to what power? To the 20th power. So that says 2 times 10 to the 20th power. Well, what is that? That is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Well, what about if I talk about 2 times 10 to the negative 20th power? Well, what is that? Well, that's 0 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Now, when I add these guys, I'm going to have to align the decimal places. So there's the decimals. So I'm going to line up the decimals and I'm going to add them. And what have I got? I've got that 2 hanging way over there to the left, and I've got this guy hanging way over there to the right. And what I have to have is enough memory, enough width in my processor to handle this huge 40-digit number. Well, what if I only have 30 digits? I'm going to chop it off 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to chop it off right there. And what have I done? I've chopped off that tiny little bit that's at the end. So when I tried to add them, what happened was that little bitty piece of the number, the little tiny number, fell off the right side of the transaction. Therefore, when I talk about underflow, here's the difference. Underflow and overflow. There's 2 important ideas coming in here. Overflow is a carry out of range. Overflow, integers are vulnerable to overflow. Integers can carry out of range on the high side, on the left side. So an overflow, obvious, doesn't happen often. When it does, it's obvious. Underflow. An underflow is a representational error on the right side of the number. It is on the tiny little side, so it tends to chop off only the insignificant digits, or what we say are insignificant. But if we can add those up over a period of time, we get something that is significant. So they can amount to, if we're doing 4 billion transactions a second, we can start talking about some real money here. Even if we're talking about millionths of a penny, if we're doing 4 billion transactions a second, we could be talking about $10 or $15 a second that we're either gaining or losing. Questions, anybody? I know I've kind of blown through this, but let's see Ganesha and Joey here today. Any questions? Stop me. Can you hear me? Somebody say boo. I don't see anything in my chat. Joey, can you hear me? Ganesha, can you hear me? Somebody send me a chat and tell me you can hear me. Okay, I hear you, Ganesha. Okay. Back to it then. We'll wrap it up here. Okay, so integer and float, the difference between integer and float. Integers are vulnerable to overflow. Float is vulnerable to underflow. Underflow is by far and away the worst one for computer scientists. Next-ish. Character data. And I think I've talked a little bit about this. Will we use only Western European characters? My recommendation to you is that you answer this question probably no. If you answer it no, you're going to add a little bit of overhead to your memory requirements or to your disk space. Excuse me. But Gmony, if you have to go back later and change it, it's really going to be tough. So my guess would be to go with the ability to use all of the full character sets of the world, meaning Japanese characters, Cyrillic alphabet, the whole thing, Korean characters, everybody gets into the act. If you just go with straight char, then you'll be limiting yourself. So here's the difference. Will we have fixed length or will it be a varying length? So here's our little table. If we have only Western European, I should have tabbed that a little bit more, only Western European, then the fixed length is char. So if I say char 16, I'm giving you 16 characters max. Well, actually, it's always going to use 16 characters. And it can only use Western European A, B, C, D, the alphabet that we use in the United States and Europe uses. And that's it. Now, the extended character set, it still gives you, if you say nchar 16, then that gives you still 16 characters, but now you have the ability to add Korean characters or Arabic characters or whatever to it. There is a cost. Nothing is free. You ever hear the word Tanstafel? Tanstafl. There ain't no such thing as a free lunch. Nothing's free. So if we go back to char and we say something is type char, now in our examples we use char and varchar. So these are strictly US characters, A, B, C, alphabet, 26 characters in our alphabet, uppercase, lowercase, and some digits and stuff like that. There is a total of 256 different possible characters I can have. Yeah. And that's the, if I go to nchar, what happens is each one of these characters, each char is represented in 1 byte. If I go to nchar, now I have doubled the amount of space I use to store the character. So if I have character data, a name, for example, a 16 character name, instead of just 16 bytes, now if it's nchar, that 16 character name costs me 32 characters to store. It's usually worth it. I recommend using nchar as opposed to plain char as a rule, unless you are absolutely certain that you're going to use only Western European characters. I mean, you might be in that world. Once you make that decision to limit it, it's not easy to change. Will your data be of varying length? Okay, varying length says I can change how long it is, so it can be 1 character or 200 or 300 characters, if I say. So once I say that it's varchar and I give it a number, it can vary up to that. Now here's my rule of thumb. If it's a small number, meaning if it's, under 50 or so. So if you have a field that is under 50, I use 64 characters as my cutoff. If it's under 64 characters, I make it a type char or nchar. Probably would make it nchar. The char and nchar are the same thing, except that nchar uses 2 bytes instead of char using 1 byte. Thus, if I have a name to which I have allocated 16 characters, it will always occupy 16 characters. It will never shrink. So if I don't put 16 characters in there, the system will pad it out with spaces for me, no problem. But it's always going to take up 16 characters. The name of the game is that there is a cost to that growing and shrinking. And it doesn't happen for free. Nothing happens for free. Remember Tonstoffel. Nothing is free. If it's going to grow and shrink, it does so at a cost, and that cost is at runtime. On the other hand, if I have something that's really, really big, to have several thousand characters, some of them might be might be over 1,000, and some of them not, I might consider going to a variable length character. This is a varchar. A varchar can be any, there is some theoretical length, but they're pretty big. They can grow and shrink within that. So if I only put 1 character in it, I only use 1 character. If I put 1,000 characters in there, then it expands to take up 1,000. Given that I allocated it to 1,000, I have to give it the upper bound. So S is the upper bound. So when I say that let me give you one here. So C so char 16 says it will always have 16 characters in it. If you don't put 16 characters in it, it still has 16 characters, pads it out with blanks. NC. Nchar. Nchar is the same as char, except that this one, each character uses 2 bytes instead of 1 byte, which gives us a lot more room. I wonder why I'm getting that. Oh, because I have a comma at the end. Okay. It's telling me I have an issue in here. Okay, sometimes it just twitches out, and it tells you that there's a issue where there isn't. Sometimes you can get rid of it by doing a go at the beginning. Anytime you're doing a create, you should bracket it with goes. I don't know what its problem is. It's just giving us problems today. Oh, nchar. Now, on the other hand, I can have a varchar. If I make it a varchar, and I make it 10,000. So that can take up to 10,000 characters. Varchar, why is it giving me a invalid type? Maybe that's too big. Okay, I guess there's a limit to what it can be. So this will go up to 1,000 characters. And if I don't use them all, it doesn't allocate them. This one, if I don't use all 16, it will pad them out with spaces. So this one will always be 16. You don't really need to worry about it, but this one will be cheaper to use than this one. So if you're always going to store a fairly small number in it, don't use varchar is the way to go. And then env, we can have an n varchar, and it can also so up to 1,000 characters. So these two can grow and shrink. These two cannot grow and shrink. If they cannot grow and shrink, they tend to run a little bit more efficiently. So don't use these unless there is some reason to in general. So if it's just a name, go ahead and allocate enough space for the name. If I need 32 bits, fine, I'll allocate 32 bits. If I have some people with very short names, I don't care. It's cheaper than allocating a varchar for a last name because most last names are going to kind of average out. And I can hit a maximum. Anybody with a last name longer than 32 bits, 32 characters, is probably used to having it truncated anyway. I get a little cynical sometimes. Talking about this. Okay, a little issue here. It is possible to have a name, but your name doesn't have any characters in it. Huh? It is possible to have a name. I have a name. My name is all spaces. Huh? My name is... Okay, what's your name? I just told you. My name is... But I have a name. I have a name. Because if I were to do something like this, if I were to assign, if I were to insert into C, for example, and I would say, C, this isn't correct syntax, but if I were to say C gets quote, quote, that is not the same thing as null. That is the string with length 0. That is not the same thing as null. This is a problem. Now, some platforms have gotten around this and some haven't. Access, for example, has not. If the character field is null, then it has no value. The string, quote, quote, single quote, is a value. It is the string that contains 0 characters. Okay, now this is one of those deals that will come back to haunt you later in your life as a database person. If you go look at your Access and you create a table in Access, a lot of you have taken Access. So it says, so when you create a table, you have to say, how long is the field? Well, okay, that's char, varchar. How long is it? The default, I think, is 50. But you set that down so that you want their name to be 16 characters. You say it's 16. Then you have a couple of other options. You say, is it indexed? Is it not indexed? That we're going to talk about later. And then one of them says allow nulls. In other words, is it required? And you can click the yes, no. Okay, the one right after the allow nulls, yes, no, allow null values. Typically, I'll always click that as no because I don't like null values. Then there's one more. Allow 0 length for a string because 0 length is not the same thing as null. And this is a hassle because I wish that they would just default it to allow 0 length and make you have to go in and change it. Suppose we have to have a character field and everybody has to have a last name. So everybody has to have a last name. So I put this constraint in there. Constraint, last name, null check, null, check, last name is not null. Pretty straightforward. Check that is not null, no problem. But what about 0 length? constraint, last name, 0 length, check that the length, len, of the last name is greater than 0. There are two different conditions. So technically, I would have the ability to have a last name that had no characters in it if I didn't have that last one. And this is a source of problems in database. This matter causes us a great deal of trouble. I have a last name. I'm not finding the names that I expect to find. And what I'm finding is that I have names in there that don't have any characters in them. Next. 94641. Okay, at this point, we're going to come to a place where database products will vary. And the syntax and semantics of time and date is slightly different. So we're going to focus on SQL Server. If you change to an Oracle platform, you're going to have some differences. They should be consistent differences, meaning that it shouldn't be completely out of the realm of something you can understand. If you can understand this one, you can probably understand Oracle too. Y2K. Video goes into detail about the Y2K deal. Essentially, we fix a point in time and call that 0, and 0 is Happy New Year of 1970. Our current date time is an integer that records the number of times that the clock has ticked since then. Now, the next thing I have to be able to answer is what is a tick? Some clocks tick faster than others. The faster the clock is ticking, tick, 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 a clock that ticks very, very fast will have a greater accuracy. Okay, but that number will get large faster. I might have a clock that only ticks once a day. In that case, I can tell you that the date is July 18th, but I can't tell you what time it is because my clock ticked at midnight and it ticks again at midnight. I can't tell you all I see is it's July 18th. So that's a clock with a low resolution. I might have a clock that only ticks once a year, and I can tell you that it's 2019, and I have to wait for the clock to tick over to 2020. Okay, or I might have a clock that ticks 1,000,000 times a second, microseconds. And in that case, I'm going to have a number that is much bigger, but I can narrow it down to a much tighter time. Let's see. So what happens is we do use Happy New Year 1970 as time 0, and a date is a number. So most database products use the term date time. SQL Server sometimes calls theirs date time too. Thus, date. If you have date, that is a date only. No time. I think date time 2 has actually been depreciated. I believe that is just date time now. I think I'm going to have to edit this one. So I think it's just date time. Date and time. So date, dates only, no time. It takes up 3 bytes. Time of day only. It is usually 3 bytes, and date time, I'm going to guess it's 6 bytes. So it's the date and the time. Gee, that one went by quickly. 6:45. Questions on dates. We're going to come back to this date business in a really quickly. I want to cover one other thing here, and let's talk about data conversion. So two types of conversions, and let me do something else before we get into this. It is possible in SQL Server to declare a variable. Now, in this little environment that we're in, this is a programming environment right here. So this is our world, and we write our programs in here, and I can declare a variable. For example, I can declare val1 as a character that can that takes 2 characters, and I don't have to put in all of the characters in it. I can just put 2 in there if I like. And this is now a variable. So all variables in SQL Server begin with the @ sign. So, and that always drives me nuts because I always forget. I just say declare val1 and then I get an error message. I'm going, why did I get that error message? But don't forget the @. So declare, and it has to be named with an @ and then it has a name. Then it has a type. So this is very similar. If we were in C, I would be saying something like char to so if I were writing in C code, I would say something like this in C++, for those of you who do C. So basically, I've just declared a variable. This variable's name is val1, and now this variable is going to stay in existence until the program either ends or I hit another go. When I hit go, it wipes out all the variables and they're goodbye. So go, essentially, usually I start with go. I don't have to here, but if I say go again, it's going to wipe everything out. So here is my variable val1 as char2. Now he's a char and he has the value 2 in him. Declare value 2 as he's an integer. An integer. What's his value? 3. Okay, so val1 has the value 2, the character 2. Val2 is an integer. He has the value 3. Now I say select. I could select val1 plus val2 as total. Now the question is, what's going to happen? I have a character and an integer. What will it do? Well, what it's going to do with that is it will do what we call promoting it. So it will promote it and I will get 5. It will change this to an integer, change it and add it to the 3, and I will get 5. Now, what would I get if I tried to do it the other way around? And I tried to say select val2 plus val1. This might change things. Let's see if it does. And it might not too. Let's see if that changes anything. So, okay, now notice that this second one, so this one, val2 plus val1 as total. Okay. Well, what did I do here? Val1 is 2, val3. Okay, so what I wanted to do was see what happens right here. And it says 5. Okay, it would not have surprised me if it had said 2 followed by 3, 2, 3. Now, what would happen if I said val 1 is x, and then I tried to add them together? On this line right here, I'm going to get an error message because it can't change val 1 into an integer to add it to 10. If I change it back the other way, it's going to happen. But this is called a cast, and this is what we're going to talk about right now. So when you cast a variable, you're saying, okay, I want you to take val 2. Well, what is val 2? Val 2 is the integer value 3. Val 2 is the integer value 3. And I want you to change that, cast it as a char 2. In other words, make it be a char 2 for just a minute. Now, it's not going to change the type of the variable, but it's going to use it as char 2. So when I say something like this, and I don't know what it's going to execute. Okay, so that's the bad part about declaring variables. You have to run the whole thing. They don't stay in existence. And down here at the bottom, here's where it is. When I say cast val 2 as char, basically he's a 3, and then I say plus. Plus means to put them together, concatenate them. We've done that, so it changed this to a 3, the character value 3, and then it concatenated that with the character value x to give us 3x. Now, casting is very handy for something like dates. So how many different ways can I talk about a date? Well, let's see. How many different ways can I write that? What about July? July 18th, 2019. Let's see. 18, JUL. 18 July 2019. Let's see. What else could I say? 18 July. If I put dashes between them. I don't know that all of these are going to work, but you can say it just about any way you want to say it. And if you cast it and say, make that a date time, it's probably going to get it right. And look at that, it did, it got all of them. So if you say cast it, you can put it in there as just about anything you want, any way that you write a date that makes any sense to anybody. The system can figure it out, and it's pretty darn good at it. Let's see, if you just give it a 2-digit year and it is after 1950, it interprets it as 1960. So if you said 60, I think it'll interpret it as 1960. If you say, if it's less than 50, it interprets it as 2000. So if you said 49, it would interpret it as 2049. If you said 51, it would interpret it as 1951. And you just have to do some testing on it. Best bet is don't just say 51, just say 2019. Or 1949, whatever you want it to be. Make sure you use the full 4-digit date, and then that way you don't have to worry about it. So notice that all of these guys have 000 for the time in there. And I see that the clock is saying that it is 6:55. Unfortunately, I have some duties tonight. So I'm not going to be able to run over. Okay, so where are we now exactly? We are on page 5, on the cast function. So we are casting. We haven't finished this page yet, so we have not finished page 5A yet. So I've introduced the idea of cast, and I'm going to introduce the idea of convert later. Convert is not a pure SQL. I like it enough. Let's see if I say it in here. I try to stay pretty much in pure SQL. The convert function is not pure SQL. It is proprietary to SQL Server, but it is so handy that I'm going to go ahead and cover it anyway. So I'm going to begin on Tuesday there, and hopefully have your tests back to you by then. Capiche? Everybody happy? Anybody alive out there?
Yes.
Okay. Who's this? Ganesha?
Yes.
Mm-hmm. Okay, I'm going to end the recording here. Unless there are burning questions. I'm going to go ahead and make the assignment, although I haven't finished it yet. And it would be good for you to go ahead and start the assignment. And then as I plow through this, I can deal with the questions. Actually, the assignment isn't that hard. This is a very big topic, a very important one, although the assignment is fairly easy. Okay, I'll see you guys then on Tuesday. So I've got to go perform some medical duties, some housekeeping duties. Okay, I'll talk to you later then. Goodbye.